Hi students, now we will discuss about elimination reactions. Uh, so before we start elimination reactions, we will see the types of organic reactions. So the reactions of organic compounds can be classified into four main types. The first one is substitution reactions, then addition reactions, elimination reactions and rearrangement reactions. The first one is substitution reactions. The substitution reactions are those reactions in which an atom or a group of atoms directly attached to a carbon in the substrate molecule is replaced by another atom or group of atoms. Okay. So in substitution reactions, the reactions in which the atoms or group of atoms present in the substrate molecule is replaced by another atom or group of atoms. Okay, for example, if we take methane and if we react methane with chlorine molecule, then one hydrogen molecule will be removed and one chlorine will be attached to the substrate molecule, that is methane, and we will get methyl chloride. So hydrogen is replaced by chlorine atom. Okay, so here replacement or substitution take place, and we call these type of reactions as substitution reactions. And the next one is addition reactions. These reactions are those in which atoms or group of atoms are simply added to a double or triple bond without elimination of atom or other molecules. So in this particular case there is no elimination of atoms or molecules, but a group of atoms or a single atom is simply added to a double bond or triple bond. These type of reactions are known as addition reactions. And the next one is elimination reactions, that we will discuss in detail. And the last one is rearrangement reactions. Rearrangement reactions involve the migration of an atom or group of atom from one site to another site within the same molecule. So the atoms or group of atoms present in the same molecule will be moving from one side to the another side. These type of reactions are known as rearrangement reactions. So you will be studying these type of reactions in detail in another classes. Today we are going to discuss about elimination reactions. So elimination reactions are those reactions in which the removal of atoms or group of atoms from two adjacent atoms in the substrate molecule to form a multiple bond. So elimination reactions are those reactions in which the removal of atom or group of atoms from two adjacent atoms, usually two adjacent carbon atoms in the substrate molecule to form a multiple bond. So in this reaction, two sigma bonds are lost and a new pi bond is formed. So sigma bond, single bond will be lost and we will get a double bond or triple bond, usually a double bond. Okay, so in this type of elimination reactions, saturated compounds become unsaturated compounds because single bond will be converted into a double bond. So saturated compounds will become unsaturated compounds. So the elimination reactions, the example for elimination reaction is dehydrohalogenation of alkyl halides. With this reaction we will explain elimination reactions. So in elimination reactions, two or four atoms or groups attached to the adjacent carbon atoms in the substrate molecule are eliminated and to form a new pi bond or multiple bond in the product. So here the general reaction is written. the alkyl halides. Here hydrogen and halide atoms are highlighted in a box, and these two atoms will be lost in elimination reaction. So adjacent carbon atoms, the the atoms which is attached to the adjacent carbon atoms will be removed, and a double bond will be formed. Okay, and these alkyl halides undergo elimination reactions with Bronsted-Lowry bases. The elements of HX are lost and alkene is formed. So what are Bronsted-Lowry bases? You have already studied in first semester. So these alkyl halides undergo reactions with the Bronsted-Lowry bases. That means the compounds which accept hydrogen atom. So the compounds which accept a hydrogen atom are known as Bronsted-Lowry bases. Hydrogen atom or protons, not hydrogen atom, actually it is protons, H+. So the compounds which accept protons are known as Bronsted-Lowry bases, and the alkyl halides will react with a Bronsted-Lowry base and form a new pi bond, an alkene, and we will get HX, which will be lost from the substrate molecule. So these elimination reactions are otherwise known as 1,2 elimination reactions or beta elimination reactions. So the example for elimination reaction I have already said, dehydrohalogenation. In the case of dehydrohalogenation, removal of the elements of HX is happening, and this is an example of beta elimination. And here you can see that alpha carbon atom is there, and alpha carbon atom is the carbon atom which hold the halogen atom. So in this particular reaction, the alpha carbon atom and beta carbon atom is labeled, and you can see that the carbon atom which is attached to the halide group, the X is denoted as, that halide is denoted as X, and the carbon atom which is attached to the halide is known as alpha carbon atom, and any carbon atom which is attached to the alpha carbon atom is known as beta carbon atom. Okay, so the carbon atom which is attached to the halide group is known as alpha carbon atom, and any carbon atom which is attached to the alpha carbon atom is known as beta carbon atom, and the hydrogen atom which is attached to the beta carbon atom is known as beta hydrogen atom, and elimination involves loss of this beta hydrogen. So in this diagram also alpha carbon atom and beta carbon atom is labeled, and the explanation for 1,2 elimination is given here. For the here a saturated compound is given, alkyl halide is represented in that particular picture in the first one, and for the double bond to form, the hydrogen must come from a carbon atom that is adjacent to the carbon atom holding the halogen atom. So if a double bond has to be formed, then one hydrogen atom should be lost from this particular substrate molecule, and one halogen atom also should be lost. So if the hydrogen atom is lost from the neighboring carbon atom of the carbon atom which holds the halogen atom, then only this particular reaction will happen, and the carbon atom holding the halogen atom is known as alpha carbon atom. Okay, here in this picture it is shown that alpha carbon atom is attached with the halogen, and any carbon atom which is attached to the alpha carbon atom is a beta carbon atom, and the hydrogen atom which is attached to the beta carbon atom is known as beta hydrogen atom, and elimination involves loss of a beta hydrogen. And elimination, when base will react with this alkyl halide, this base will abstract the hydrogen atom, and hydrogen will be lost as a proton, leaving its 2 electrons in the substrate molecule, and that will form the double bond. Here 2 examples are given, and in some cases dehydrohalogenation yield a single alkyl, and in other cases sometimes they yield a mixture. And to predict which product can be formed in a given reaction, we have only to examine the structure of the substrate. We can expect an alkene corresponding to the loss of any one of the beta hydrogen atoms. Okay, so here 2 examples are given. The first one is N-butyl bromide. So as we have discussed, the carbon atom which is attached to the bromine atom, means halogen atom, so that will be denoted as alpha carbon atom. So the carbon atom which is attached to this particular alpha carbon atom is known as beta carbon atom, and hydrogen will be lost from this beta carbon atom. Then only double bond will be formed. And in the first example, you can see that bromine is attached to the first CH2 group, first carbon atom. So only one option is there. Only one beta carbon atom is there in that particular structure. The carbon atom which is attached to the carbon atom bearing bromine. Okay. So from that carbon atom, hydrogen will be lost, and we will get one butene as the product. That will be the only product when N-butyl bromide react with KOH in alcoholic solution. And in the second example, you can see that the structure is of secondary butyl bromide, and secondary butyl bromide when react with a strong base in alcoholic solution, there also the elimination will occur, and we will get butene as a product. And in this particular case, if we see the structure of secondary butyl bromide, the bromine atom is attached to the carbon atom, and on both sides of that particular carbon atom, other carbon atoms are present. So the carbon atom which is attached to the carbon bearing halogen is known as beta carbon atom, and from that hydrogen is going to lose. And in this particular structure there is 2 beta carbon atoms are there, and from any of these 2 beta carbon atoms hydrogen may be lost. So 2 options are there. We will get one butene or 2 butene as the product. So if you see the structure, you will come to know how this particular reaction is occurring. So since in this particular structure 2 beta carbon atoms are there, so there is 2 possibilities for the formation of butene. So either it will be 1 butene or it will be 2 butene. Okay. And if these 2 alkenes can be formed, then 2 butene is the chief product. And this particular reaction is based upon Saysev rule that we have already discussed. And we have seen the elimination reactions and the examples. So these elimination reactions are characterized by three steps are there. The first one, the substrate contains a leaving group that leaves the molecule taking its electron pair with it. So halogen is one of the example for a leaving group, and the particular molecule or substrate contains a leaving group that leaves the molecule, but they take their electron pair with it, and in a position beta to the leaving group. That means in a position beta to the halogen group. For example, okay, the substrate contains an atom or group, usually it is hydrogen, that can be extracted by a base leaving its electron pair behind. Okay, so the first case is a leaving group is there and another group is there. These two groups will be leaving the molecule, but a small difference is there. The leaving group, that means the halide groups will leave the molecule taking its electron pair with it, but the other one, in a position beta to the leaving group, the substrate contain an atom or group, usually hydrogen, that can be extracted by using a base, a strong base, leaving its electron pair behind, and this particular reaction is brought about by a base. These are the characteristics of an elimination reaction. And now we will discuss about the kinetics of dehydrohalogenation or duality of mechanism. With a concentrated solution of a strong base, that means we have discussed that for this particular reaction to occur, the reagent is a strong base in alcoholic solution, and if the concentrated solution of a strong base is used, then dehydrohalogenation follows second order kinetics. Now we are discussing about the kinetics of dehydrohalogenation. Kinetics means rate of reaction. So these particular reactions are occurring, in which rate it is occurring, that we are dealing in this particular kinetic section. So if we are using a strong base, then dehydrohalogenation follows second order kinetics. Second order kinetics means the rate of alkene formation or the product formation depends upon the concentration of two substances. Two substances means in this particular reaction we use an alkyl halide and a base. So in this particular second order kinetics, the rate of the alkene formation depends upon these two substances. So based upon the concentration of alkyl halide and base, the reaction is occurring. So this second order reaction is observed for all classes of alkyl halides, and the rate can be represented as rate is equal to K, that is the rate constant, into concentration of alkyl halide into concentration of a base. So from this particular reaction we could find that the rate is directly proportional to the concentration of both the reactants, that means the substrate, that is the alkyl halide, and the reagent, which is the base. And it proceeds along a series of substrates like primary, secondary or tertiary alkyl halides, and if we reduce the strength or concentration of the base used, then this particular dehydrohalogenation follow first order kinetics. So usually primary alkyl halides undergo second order kinetics, and if we proceed these reactions through primary to secondary to tertiary, then it will move from second order to first order kinetics, and if we reduce the strength or concentration of the base, then the dehydrohalogenation will be first order kinetics. The first order kinetics means the rate of elimination depends only upon the concentration of alkyl halide. and it is independent of the concentration of base. So in first order kinetics, the elimination rate depends only on the concentration of alkyl halides and independent of the concentration of base. Then we can express the rate equation as rate is equal to K into concentration of alkyl halides. Since this particular first order kinetics depends only on the concentration of alkyl halides, we are considering the concentration of alkyl halide only in the rate equation. So rate is equal to K into concentration of Rx. Rx means alkyl halide. And in general, this first order reaction is encountered only with secondary or tertiary substrates. That means secondary or tertiary alkyl halides, and if the solution where the base is either weak or in low concentration. In these two conditions, this dehydrohalogenation follows first order kinetics. And these type of kinetic behavior can be explained by two different mechanisms. So this first order kinetics and the second order kinetics can be explained by two different mechanisms of dehydrohalogenation, and these mechanisms are named as E2 elimination reactions and E1 elimination reactions. First we will discuss about E2 elimination reactions, and E2 elimination reactions involve a single step process. So E2 stands for bimolecular elimination. That means in E2 elimination reaction, the rate of reaction depends upon the concentration of the substrate and also the base. So since it is a bimolecular elimination, it is represented as E2 elimination reaction. And E2 elimination reactions are second order reactions. That means rate of the reaction depends upon the concentration of substrate and nucleophile. Nucleophile means example is base, and it is a one-step process in which the abstraction of the proton from the beta carbon atom and expulsion of the halide ion from the alpha carbon atom occurs simultaneously. So this dehydrohalogenation is an example for elimination reactions, and this dehydrohalogenation may occur by first order kinetics or second order kinetics. If we use primary alkyl halides and the concentrated solution of bases, then the reaction will be second order will follow second order kinetics. And if the concentration of the base is less or it is a weak base, and if the alkyl halides are secondary or tertiary, then there is a chance for the first order reaction. So based on these two kinetics, we have classified elimination reactions into two types. The first one is E2 and the second one is E1 reactions, and this E2 stands for bimolecular elimination. That means the reaction depends upon the concentration of the substrate and the base, or we can say a substrate and a nucleophile. Nucleophile means a group which attract a positive charge. Okay, and this E2 elimination reactions are one-step processes in which the abstraction of the proton, because in elimination reaction and particularly if we take dehydrohalogenation, there is a removal of hydrogen halide. So hydrogen has to be removed and halogen has to be removed. And in E2 elimination reactions, it is a one-step process. That means the abstraction of proton from the beta carbon atom by the base and the expulsion of halide ion from the alpha carbon atom occurs simultaneously. And now we will discuss about the E2 mechanism. As I have already said, this reaction involves a single step. that means base pulls a proton away from the carbon, that means the beta carbon atom. Simultaneously a halide ion departs and the double bond forms. And as we have discussed in the characteristics of elimination reaction, this particular leaving group, that means leaving group is halogen in this particular case, this halogen takes its electron pair with it, but hydrogen leaves its electron pair behind to form a double bond. Okay, the first step is the base, which is the reactant that will pull a proton from the beta carbon atom, and simultaneously a halide ion departs and double bond is formed. And these are the electronic changes that will happen in dehydrohalogenation, and these all reactions, that means the abstraction of the proton and expulsion of this halide ions will take place in a single step, that means via a single transition state. So this is the representation of E2 reaction, E2 elimination reaction. It is a bimolecular reaction. In this case you can see that a base is attacking hydrogen, so hydrogen will leave its electron with the carbon atoms, and it will be lost as a proton, and hydrogen halide will be formed, and the protons will move to the CC bond, and at the same time the halogen atom will be expelled from the alpha carbon atom, and the halogen atom will take those two electrons with it, but since the hydrogen atom leaves its electron, a double bond is formed between the alpha and beta carbon atom, and alkene is formed. And here one example is also given. And in this particular transition state, two bonds are being broken. That means CH bond is broken and CX bond is also broken. And from where does this particular energy for this bond breaking come from? And this particular energy will come from bond making. So that means the formation of the bond between the proton and the base, and formation of the pi bond. So in these two processes, since the bond making process is an exothermic process, exothermic process means this will liberate heat energy. So this energy will be used for the breaking of CH bond and CX bond. So there is two bond breaking, that is CH bond will be broken and CX bond will be broken. For that particular breaking of the bonds, the energy will be obtained from the bond making processes. That is, the bond with, between hydrogen and base will occur, and also a double bond is formed between carbon-carbon single bond. So these two bond making processes are exothermic process, and it will release energy, and that particular energy is utilized for the breakage of other two bonds. So thus the E2 reaction is a bimolecular reaction. That means the two molecules are involved in the rate limiting step, and it involves a second order kinetics because the two molecules must come together for the reaction to occur. And rate is represented as K into concentration of base into concentration of substrate. This is an energy diagram for an E2 reaction, and in this case, in the E2 reaction there is a transition state. That means the CH bond and CBr bonds will be breaking, and base will form a bond with hydrogen, and a double bond will be formed. That is known as the transition state. Here you can see the partial bond forming and bond breaking from this particular transition state. So this is just a representation of energy diagram. And these are some examples for strong bases. So KOH, potassium hydroxide and sodium hydroxide, it is already known for you. And some other bases are lithium hydroxide, cesium hydroxide, calcium hydroxide, etc. Now we will discuss about even elimination reaction. It is a unimolecular elimination reaction and it follows first order kinetics. That means the rate of elimination reaction depends only on the concentration of the substrate. In the case of E2 elimination reactions, the rate of the reaction depends on the concentration of the substrate as well as the concentration of the base added, that means the reagent. So that's why the reaction was bimolecular reaction, because both the reactants participated in the rate limiting step, and it was a single step process. And in this case the rate of elimination reaction depends only on the concentration of the substance. That's why it is known as a unimolecular elimination reaction and it follows first order kinetics. And we can designate this elimination reaction as even elimination reaction, because E represent elimination and 1 represent the reaction is first order, or it is a unimolecular elimination. Now we will discuss about the even mechanism. So how this dehydrohalogenation is occurring with this particular mechanism, what may be the possibility. So in this case also the electronic changes, that means the bond breaking and bond making are the same as in E2. That means the hydrogen and carbon, beta carbon and hydrogen bond will be breaking, and alpha carbon and halogen bond, that bond also will be breaking, and in between the alpha and beta carbon atoms the new bonds are forming. That means a double bond will be formed. All these electronic changes are same, but in even mechanism these processes are taking place one after another. So simultaneously it is not happening as we have discussed in E2. But they are taking place one after the another, and it follows first order kinetics. That means overall reaction is determined only by the slow first step. So it has two steps, and based upon the first step, that is the slowest step, and based upon the particular first step the overall reaction is determined. And in the first step only one reagent is there, that means the substrate will be there, and that's why it is a first order kinetics. And the even involves two steps. The first step is the substrate undergoes a slow heterolysis to form halide ion and a carbocation. So alkyl halide, that is the substrate which undergoes a slow heterolysis process. Heterolysis process means in this particular process one of the atoms acquires both of the bonding electrons when the bond is broken. So in the first step the substrate undergoes a slow heterolysis process to form halide ion and a carbocation. So from the alkyl halide, the halide ion is leaving and we will get a carbocation. But this process will happen by heterolysis. Heterolysis means the atom which is leaving will acquire both of the bonding electrons when the bond is broken. That means when this particular halide ion will leave, that time it will take those two electrons with it, and a positive charge will be remaining on the substrate. That's why we get carbocation. And this is the slowest step in this particular even elimination reaction. And in the second step the carbocation rapidly loses a proton to the base and form the alkene. So in the second step only the base will come into picture. In that case base will attack the proton and this proton will be lost and we will get alkene as the product, that is the elimination product. And this is the even mechanism. In the first step the substrate undergoes a slow heterolysis process to form halide ion and a carbocation, and in the second step the carbocation reacts with the base and it rapidly loses a proton to the base and form alkene. So in this particular slide you can see the reactions. The halide ion is leaving, that time it will take those two electrons and we will get a carbocation or carbonium ion, and this first step is very slow, and in next step the carbocation will react with base and a proton will be lost and we will get an alkene. And when this carbocation is formed, in the first step a carbocation is formed, and this carbocation may combine with a nucleophile, that is a possibility, or this carbocation can undergo rearrangement to form a more stable carbocation, or there is a elimination of a proton by the reaction with a base to form alkenes. And another options are also there for this particular carbocation. In this particular reaction we will be explaining about the elimination of a proton to form alkenes. So other options are also there, like combining with a nucleophile, rearrangement to a more stable carbocation, etc. And the overall rate of reaction is determined only by the slow first step, that is the formation of a carbocation, and it is by the removal of halogen atom or halide group. And the rate determining step involves only substrate, and the rate depends on the concentration of substrate. So this base doesn't have any role in this rate limiting step, and the rate of even reaction is independent of the concentration of base, because rate determining step does not involve base. And we can represent rate as it's already given, rate is equal to K into concentration of the substrate, and thus even is an elimination unimolecular elimination reaction.